Hi, well, I got a new toy recently. This is yet another X-ray machine. This is a Faxitron system which is designed for doing X-rays of things like biological specimens. About the size of a small fridge. Not ridiculously heavy. This only goes up to 35 kV, so it doesn't have lead shielding. It uses just I think steel and stainless for the shielding, because that's all it's needed to go through to protect against those lower energy X-rays. The two really nice things about it, it's got a microfocus tube, which means the effective spot size is something of the order of 20 microns, which means you can get super fine detail. It's also got a CMOS detector, which has got a resolution of 20 lines per millimetre, which means that for an object placed right at the sensor, you get sort of 20 lines per millimetre resolution. But because the beam effectively diverges, if you place objects higher up, you get effectively geometric magnification up to I think about 10 times, so you can get really detailed X-rays of really small objects, which of course is super interesting for doing electronic stuff. I'm told these originally cost about $60,000. I paid quite a lot less than that, but not peanuts. So this is dated about 2008, so it's not all that old. And looking at the log files, according to the logs on the software, it's only done 700 exposures, but that it may have been reinstalled, so that may not be the original count. But it's only in very good shape and works quite nicely. Now, it came on this big trolley with the monitor and everything. There's a PC that sits in the bottom. Strangely, also there was this huge, great, heavy medical isolation transformer, which is sat here. I think actually the main purpose of that was probably to wedge the PC in, because okay, you can understand why you'd use an isolation transformer on something that might get connected to a patient, but for a standalone X-ray machine it seems just completely unnecessary. So I've really no idea why they put that in there. Okay, it's got a convenient sort of bunch of extra connectors on the back, but I'm sure there's cheaper ways of splitting the mains into 3 IC connectors. A little bit ridiculous. Now, the main cabinet does have a user interface, but this system, everything's controlled from the PC. You don't actually need to touch this panel at all, but you can manually enter voltage. For example, there's versions of this system, for example, without the camera, that you could use with film. So you've got all the settings for KV and exposure time. There's also AEC, which I think that's to automatically adjust the exposure versus the current for a given sort of overall exposure on film, and there's all sorts of like set up various preset settings and so on, but nothing hugely interesting on the front panel. Right, so on the top of this thing, got a little fan in there, big power supply along the back. Looks like, I think it's a dummy load resistor to provide some minimum load for the power supplies. Some multi-output power supplies like that. So there's like a little cap across there, presumably for a bit of noise filtering. And here we've got the sort of main control board here and the front panel, which is sort of just the membrane switches behind it. A few various oddments. There's a little piggyback board there with a couple of opto isolators. I'm guessing that's probably something like an isolated serial interface. There's a lithium backup battery there. There's an NXP 80C 552 processor, which is a fairly old 8051 based microcontroller. One thing I thought was a bit dodgy, this connector here pops out very easily. There's no real positive latching. It sort of seems to really, it doesn't take much, so a little bit vulnerable to that falling out. It's a little bit dodgy for a piece of kit that's this expensive. Nothing particularly exciting on here. Some NXP LED drivers to drive the displays, various other odds and ends. Obviously in the middle, this is the actual X-ray tube assembly. And in here we've got the power supply, 35 kV power supply. Big warning, warning you on radiation and high voltage. And there's a control board here, so that's going to be doing some of the control of things like the voltage and current regulation, but also because the microfocus X-ray tubes use magnetic focusing, this is probably going to be doing some of the driving of the focus coils, etc. The coils secured down with these sort of security-ish screws, but that's no major issue. On the side here there's some monitoring outputs, so you've got 1 volt per 10 kilovolts and the tube current 1 volt per milliamp outputs for testing. I'd imagine everything inside this enclosure is probably made by the X-ray tube manufacturer as a sort of custom version for Faxitron to then use in their system. So if we look under here, incidentally this cover isn't lead, it feels like stainless steel because it's only 35 kV. That has very low penetration through metal, so you don't need lead to do the shielding. So here we have the actual tube. It's got this high voltage feed through here, and the actual tube, this feels like it's coated in something like silicone, so they probably just encapsulated the whole thing in silicone to avoid any high voltage issues. Again, at 35 kV, they probably didn't think it was worth doing oil, which is all quite messy, but also because the actual tube power is quite low, they don't need oil for cooling. The power's limited to 12 watts on this because of the small spot size. And this tube is a TFX 8050, which apparently will go up to 50 kV, but so this setup only goes up to 35. And you can see these wires coming out the bottom. There's more than just the 2 filament wires. There'll be some extra leads for the focusing coils. Pity we can't X-ray this tube. Actually, that would be quite a fun thing to see, but bit of a problem there. And actually we've got this air ducting going out. I'm assuming, I can't quite see, but I would imagine there's an airflow path through the front of the tube for the air to actually come out down there somewhere. But it's interesting, we've got a filter here, but we've also got this additional baffle here. Again, I would assume that's just to provide some X-ray shielding so you don't get X-rays coming through the fan holes. So that's going to be handling probably sort of some of the voltage and current regulation, because the other issue with microfocus tubes is you need to reduce the current as you increase the voltage to limit the power dissipation at the spot to avoid damage. But I'd imagine this is probably also doing some sort of control of the spot size. I don't know whether that would be open or closed loop. I don't really know much about that stuff. This is made by a company called True Focus Corporation. Lots and lots of warnings, X-rays and stuff, but also because it's a soft X-ray device, it's got a beryllium output window, so it's warning about the toxicity hazard of the beryllium on there. One thing I was a little bit surprised at, as far as I can tell, there doesn't seem to be any interlocks on this cover, either on the, I probably wouldn't expect one on here, but even this top cover, which just comes off with 4 screws, I can't actually see any sign of any interlocking to stop you just pulling all the covers off and firing it up, which is I thought slightly odd. Right, I managed to get this board out. This is actually made by Faxitron, not the tube manufacturer, but interesting thing is that it looks like this tube is electrostatically focused rather than magnetically. So you've got these 3 1.5 kV power supply modules. Looks like each one's got a sort of driver transistor, so maybe so quite often these high voltage modules, the way they work is that you adjust the input voltage to control the output voltage. There's a bunch of MOVs there and some resistors. And this tube is different. The physical layout of this tube is different to the microfocus things I've been able to find information on the net, in that most of those show sort of tube with the output coming out the end, whereas this comes out the side. So it could be this has got a different physical arrangement of the electrodes inside. But this feels like fairly sort of silicone-y insulated stuff. So it looks like this is using some sort of electrostatic means to reduce the small focus spot, rather than well, there might be some magnetics in there as well, I don't know, but other than that there's nothing particularly interesting, just some various analog control stuff on there. Right, so inside the cabinet we've got this double interlock thing which contacts these 2 micro switches to make sure it turns off when you open the door. That's the actual aperture where the X-rays come out. That will be a beryllium foil window, which is down at somewhat fragile. You certainly do not want to be poking your fingers at that. And in here there's a couple of these line lasers, which give you a nice handy cross to show you where the the sensor is, which especially when you're working on shelves up above, it's actually quite difficult to judge where it is, so just having that cross mark makes life a little bit easier. There's the shelf positions for putting the sample. It's got a number of different positions to achieve different magnifications, because if you consider you've got this point source up here producing an image on the sensor down here. If you're sort of right down here, you're going to get a 1:1 magnification, but as you go up, it's going to effectively make the image bigger as the shadow gets bigger. And this is the actual sensor down here. These do come with different sizes. This is a 50 by 50 millimeter. There's also, I think, 100 and maybe 120 by 120s, which are probably even more ridiculously expensive. This sensor has a 50 micron pixel pitch. So the overall resolution is 1056 by 1056, and the centre is basically a big photodiode array with a scintillator over the top of it that glows when X-rays hit it. The photodiode array is going to be quite sensitive. I did a quick test with some scintillator materials in here, and even with the camera on night view mode, I couldn't see any light at all from it, because it's only a 300 microamp beam current. So there's going to be some quite sensitive photodiodes and amplifiers and so on in here. And this just sits on this bottom plate here. It's quite interesting, there's an interlock switch on this plate. I'm not quite sure why, because you'd have to have the door open to get in here. But this is obviously something that a user is potentially likely to need to get access if they want to put a different camera in or replace the camera. Under here we've got a power supply board, there's some DC-DCs and some linear regulators. I'm guessing what they may have done is, obviously because this thing is very sensitive, they want a nice low noise supply, so they maybe used DC-DCs there and stuck some linear regs on the outputs of them just to get a nice clean output. And it may also be that they're converting the voltage. They've used a few different makes of cameras over the years in this product, so it could be that this Hamamatsu camera, which is one of the newer models, maybe uses different supply voltages to what they originally used, so perhaps they're using the DC-DCs to convert that as well. Not much else. There's a tiny little fan there. I can't really see that fan's going to do a lot really on something this size. Seems a little bit pointless. And these are just the back panel connectors, the RS232 for the X-ray control on the USB. This is USB to the camera. Interestingly, this thing is a back-to-back USB-A connector, so that the actual external cable is a USB-A to A, which is a bit messed up. That really should be a sort of A to B adapter. I don't quite know why they did that. It looks fairly big, so there might be some filtering in there as well. And so this is the actual camera, which we'll unplug and take a look at. Right, so this is the camera module. I think the reason for this shape and size is obviously in some applications this will be replacing an X-ray film cassette, so I'd imagine the form factor is designed to make it easy to replace old film systems with this in the same mechanical form factor. The USB Mini B connector there, the ground connection, and a very expensive Fisher or Limo connector. I believe that's for external triggering. Because again, if you're using it in conjunction with an old film system, you might need to manually tell it when to take the photo, and that deconnector is for power. Right, so this is the actual sensor module. Interesting, the mounting plate is actually designed to accept the larger camera, and it's just masked on the inside plate. This is some sort of fiberglass type window material. Again, the front of this sensor, it looks like some sort of, it actually looks like carbon fibre, whether it is or not, but it's got that sort of feel of fiberglassy composite type material. Alright, so this is what we see when we pull the lid off. Big PCB around the outside, big multi-way connection. The actual sensor is under here. This has got lots of sealed screws and warranty seals, so I'm afraid I'm not going to pull this apart. I've no idea what these cost, but I have no doubt it's quite a few £1,000. Let's see if anyone's got a dead one of these they'd care to donate for a more extreme teardown. You know where to send it. But I'm not taking this one apart, sorry. Now, of course, because this is designed to be used in an X-ray environment, this metal shield isn't just normal. Your normal sort of shielding that you see in a lot of products. It's about 1.5 millimeters thick, so this is obviously to prevent the X-rays affecting the electronics in here. Nothing really too surprising on this board. Got some front-end amplification here, some quad op amps, a bunch of analog multiplexers, and down here we've got 8 LTC 1748 of these, which are 14-bit 6 megasample per second. Then we've got the connectors here with some filtering, and there's a couple of FPGAs. And these cans, if you look at, there's one unpopulated one, these look like they're probably just the oscillators, possibly a switching regulator or something inside there just to keep it shielded, because again this is all very low noise stuff. So I want to keep everything as quiet as possible. This is probably an umpteen layer PCB. A few configuration switches, looks like some for setting, like flip X and Y directions, that sort of thing. A few more little bits and pieces, a few unpopulated things. Unfortunately I can't get this PCB out easily because this needs to slide sort of horizontally out of that connector, and there isn't room to get it out without taking the sensor out, and the mounting screws for the sensor are glued, and there's glue sort of that extends onto that cover, so I don't want to risk taking those screws out and doing any damage to that sensor, I'm afraid. But I doubt there's much on the other side other than decoupling, but nothing sort of hugely exciting. Take a quick look at the data sheet to give us a rough idea of how this works. It's showing this as a sensor board now. It's not clear whether this is the entire photodiode array is a single sort of piece of silicon, or whether it's made up of several sections. But it looks like there's some sort of amplifier array. There's some of the sort of demultiplexing amplifiers. It looks like there might actually be one amplifier for each column. So it shows 8 arrays with 132 channels each, and there's obviously some onboard multiplexing in there. Then it's just showing the rest of the stuff that we could see on the PCB, sort of buffer and processing amplifiers, A to Ds, and then all the stuff in the FPGAs. And obviously, because these detectors are a honking great piece of silicon, they are going to have some defects in there, and they're expensive enough without having to reject any that have many visible defects. The datasheet says a maximum of 10 full lines as defects, and I found a defect map in the software. There's probably some sort of calibration procedure. So this is the image showing the defect on this sensor. Right, let's have a look at some images. This is a 2-layer PCB. It would just about penetrate copper foil on PCBs, but not much else. Any steel or anything just doesn't go through at all at the 35 kV, which is probably the most sort of limiting factor on this thing. This is a calculator. This is using mostly conductive silver ink, so you get it's sort of semi-transparent. This is a flex out of a camera. This is a TFT display, again on flex. You can see the glass attenuates quite a lot. This is a micro SD card with some quite interesting patterns in there. This is the chip on an RFID card. This is a fairly modern SD card, showing that there's only about half of the card has electronics in it. And this is a close-up of the chip in that card, showing some very fine bond wire detail.